Empiezo de nuevo. Muchas gracias por su presencia en esta actividad. Como decano de la Facultad de Odontología de la Universidad de Chile, siento un gran orgullo de inaugurar en nuestro campus, el Eloíso Díaz, constituido por la Facultad de Medicina, el Hospital Clínico de la Universidad de Chile, la Facultad de Odontología y la Facultad de Ciencias Químicas y Farmacéuticas, que están entonces haciendo un esfuerzo por trabajar en conjunto en las actividades que podamos compartir. De hecho, estamos en este momento en Ciencias Químicas y Farmacéuticas, ¿no? Estamos entonces inaugurando la tercera versión de la Escuela Práctica TYAN. Este es un evento internacional organizado en colaboración con la Academia Mundial de Ciencias, cuyo propósito es fomentar el aprendizaje práctico de estudiantes de pre y posgrado en áreas de la salud, biotecnología, ciencias ambientales. Desde el 11 al 15 pueden ser testigos de las presentaciones de importantes académicos y científicos de distintos países: Argentina, Estados Unidos, Brasil y Chile. Quiero saludar especialmente a la doctora Andrea Paula y a la doctora Paola Llanos, quienes conforman parte del comité organizador de este evento, quienes han desplegado su mayor esfuerzo para que esto salga de la mejor manera posible. Deseo el mayor de los éxitos durante la organización de esta jornada, esperando que se puedan reforzar lazos entre todas y todos los participantes en esta actividad, de modo de potenciar nuestras capacidades en investigación en todos los aspectos que vamos a analizar. Muchísimas gracias entonces, y damos por inauguradas esta jornada. Muchísimas gracias.
Bueno, muchas gracias a todos por su presencia. Decana de la Facultad de Odontología, doctora Irene Morales; decano de la Facultad de Medicina, doctor Miguel O'Ryan; director del Instituto de Ciencias Biomédicas, doctor Emilio Herrera; directora de Comunicaciones de la Facultad de Odontología, Cecilia Espinosa; director de Investigación de la Facultad de Medicina, doctor Leandro Carreño; distinguished guests, esteemed colleagues, staff from the Eloísa Díaz Campus, muchas gracias a todos por su apoyo incondicional en la organización de este evento. Nosotros estamos muy entusiasmados con esa escuela práctica. Tendrán varios eventos. Yo a continuación voy a explicar un poco más de los detalles de la escuela. Sin embargo, Franco Cabrerizo, quien representa a la TUAS y la TYAN aquí entre nosotros, nos va a dar una pequeña introducción de qué se tratan esas escuelas, las versiones anteriores, ese panorama general, en qué países fueron llevadas a cabo, y luego yo voy a introducir nuestra escuela con los detalles para que todos conozcan. Van a haber varias actividades en paralelo, entonces tenemos que entender un poco el programa, que es complejo, y van a continuación tener esta idea. También agradeceré a la TUAS, la CREP, a la TYAN, a la Academia Brasileña de Ciencias, a la Academia Chilena de Ciencias, a la International Science Council y a todos los sponsors involucrados por este apoyo incondicional a la realización de la escuela. Franco, por favor, muchas gracias por tu presencia acá y te dejo con tu pequeña presentación.
Muchas gracias, Andrea. ¿Se podrá acercar? Antes de comenzar, cuando Andrea me pedía que diera unas palabras, pensaba un poquito sobre qué hablar y me pareció oportuno, aprovechando la presencia de las autoridades, aprovechando también la presencia de colegas y obviamente de los estudiantes, me pareció oportuno contar un poquito las experiencias anteriores, en primer lugar para entender el marco en el que se generaron, compartir con ustedes situaciones o experiencias relativamente similares y muy brevemente, ¿cuál fue el aprendizaje de algo que, si bien es muy joven, es un proyecto que comenzó, ¿se puede pasar para atrás? ¿Sería este? ¿Cuál? Estos. Bien, ahí. Es un proyecto relativamente joven que comenzó hace no más de 2 años, pero que creemos que tiene mucha relevancia o mucha fuerza y que puede impactar de manera significativa en países como los nuestros, ¿no? En países denominados del sur global. Comienzo con un slide bastante desprolijo, pero simplemente para que les quede una foto de en qué consiste esta red de TYAN. Es un programa que funciona dentro de la Academia Mundial de Ciencias y quiero que nos quedemos con esto es un pointer, quiero que nos quedemos con este mapa general. Estamos hablando de, ahí arriba, algo así como 400 miembros, fundamentalmente teniendo esto, de más de 85 países y cubriendo alrededor de 11 o 12 áreas del conocimiento general. Esta enorme diversidad también en cierta medida nos animó a pensar este proyecto del que hoy forma parte la escuela, ¿no es cierto? La red tiene varios programas, 4 programas de financiamiento, pero nos vamos a enfocar en este de aquí, en el programa Teach. Esto no funciona muy bien, en el cuarto programa, que es un programa enfocado en la educación de la ciencia, ¿no? Y en promover en distintos niveles, en distintas condiciones, la transferencia del conocimiento en el marco de la educación. Y ahí, ahora viene, entonces, en ese contexto empezamos a pensar cuáles son las necesidades, y durante la pandemia aprendimos que, bueno, los cursos eran relevantes, eran muy importantes, la virtualidad, pero sin embargo se puso en manifiesto la necesidad que tenemos en todos nuestros países, y es la falta de experimentación. Nuestros estudiantes, nuestros alumnos, incluso alumnos de doctorados, en algunos casos, pensemos también que es un programa orientado a los 85 países que nos representan y alguno más, con lo cual hay heterogeneidad y diferencias en la situación o en el desarrollo de la ciencia y la tecnología en cada uno de los países, pero en términos generales se comparte un punto o una falencia, una necesidad clara, que es la de los alumnos experimentar. Es lo que lo llamamos hands-on activities, ¿no? Actividades de laboratorio. Y en ese marco empezamos a pensar en movilizar instructores, miembros de la red con cierto expertise a distintas regiones, y comenzamos por Bolivia, y esa fue la primera escuela. La primera escuela fue por Bolivia, hicimos una especie de exploración donde, emulando un formato similar al que va a contar Andrea, que va a ocurrir acá, se enviaron 5 instructores para dictar 5 cursos paralelos en temáticas muy diferentes. Ustedes pueden ver que hablamos de fisiología de plantas, tecnología de alimentos, fotoquímica, espectroscopías, modelos de experimentación animal. El objetivo fue explorar, bueno, cuál es la necesidad real ahí, en ese lugar en particular. Fue en La Paz, en Bolivia, sobre qué áreas temáticas pueden tener más interés, más atracción, sobre cuáles, pensando también en el futuro, ¿no? Sobre qué áreas desarrollar. El aprendizaje de esa primera escuela hablaba de la necesidad de estos cursos de experimentación. Durante los últimos años, si ustedes buscan un poco en la literatura, van a ver que se hace referencia a esta necesidad real, y porque sirve para construir capacidades, y eso es otro término que me gustaría ahora redefinir o que repensemos entre todos. Esa escuela tuvo esta composición, para que vean, en una convocatoria de poco menos de 2 semanas, tuvimos alrededor de 450, 430 preinscriptos. O sea, eso lo pongo de manifiesto como para de nuevo enfatizar en la necesidad real de este tipo de actividades, o el interés. Estamos hablando de ofrecerle a estudiantes la capacidad de interaccionar de nuevo, de experimentar en el laboratorio, pero interaccionando con colegas extranjeros, desarrollando y explorando nuevas habilidades. Es algo sumamente interesante. Algo parecido ocurre aquí, ya compartiremos los números, pero naturalmente fue una escuela exploratoria. Por la limitación de recursos solamente pudimos aceptar a 100 alumnos, alrededor de 100 alumnos, y así lanzamos la primera escuela, con esos 5 cursos paralelos. Y empiezo a repensar, yo hablé de construir capacidades. Creo que en realidad es momento también de que quizá acuñemos otro término, empezar a pensar más que en construir capacidades. En nuestro caso deberíamos empezar a hablar de redescubrir capacidades o descubrir capacidades, porque básicamente una de las cosas que aprendimos cuando estuvimos allí es que nos encontramos con colegas realizando trabajos, tareas sumamente interesantes, de muy buen impacto, de muy buen nivel, desconectados, quizá desconectados con la red internacional, muchas veces, que también nos pasa en nuestros países, hablo desde Argentina, desconectados de la red local. Muchas veces estamos orientados en qué es lo que está pasando afuera, pero nos olvidamos que alrededor está ocurriendo algo similar, y esta escuela sirvió como disparador para catalizar ese tipo de interacciones, y por ejemplo, planteamos la segunda escuela, con el apoyo del rector, estaba el rector aquí, el rector de la Universidad Mayor de San Andrés, quien inmediatamente entendió la importancia, la relevancia de este tipo de actividades y comenzó y propuso firmar un convenio de entendimiento con TYAN para generar y dar lugar a nuevas ediciones. Entonces al año siguiente ocurrió la segunda escuela, y ahí van a ver que hay una pequeña, más allá de los afiches y de los colores, van a ver que hay pequeñas incorporaciones, además de los instructores, que en algunos casos se repiten, algunos instructores nuevos, hay caras adicionales que en todos los casos son exalumnos de la primera escuela. Se identificaron aquellos alumnos destacados o de más interés, algunos de ellos eran profesores en la escuela. Voy a contar brevemente un caso interesante de una de las alumnas que también se sumó como constructora en la segunda edición, que es una experiencia interesante. Pero de nuevo, es descubrir qué es lo que había, empezar a conectar con colegas locales que tienen las capacidades para transmitir, para generar el conocimiento y establecer nuevas escuelas. Pensábamos en esta breve introducción también, para más que palabras, también mostrarle algunas fotos, algunas imágenes para que vean de qué se tratan los alumnos en el laboratorio. Esto corresponde a la segunda edición, donde a pesar de unas fuertes inclemencias climáticas, en esa semana tuvimos lluvias extremadas, digamos, muy, muy grandes, con anegamientos de carreteras, rupturas de puentes y accesos centrales, pero aún así los estudiantes buscaron la manera de llegar hasta el predio de la universidad para ejercitar y para tener las prácticas. Se firma el convenio, a partir del cual, y con esta segunda escuela, identificamos también la necesidad de desarrollo local. Este es el caso que les quería comentar, también para tener una idea de cuáles son los posibles resultados, el impacto, o qué puede surgir a partir de este tipo de escuelas, que definitivamente algo similar va a ocurrir aquí por la sola razón, el solo hecho de juntar colegas, científicos y estudiantes. Nuevas ideas y necesidades surgen. Les contaba, este es el caso de Zdenka. Ella hizo el doctorado en Italia. Cuando vuelve a Bolivia, con 2 hijos, después de la maternidad, fue muy difícil reinsertarse. Estamos hablando de una persona con una capacitación enorme, había hecho su carrera de grado, su doctorado en el exterior. Decidió participó en el primer curso, en la primera edición, tenía enormes capacidades, por eso hablo también de redescubrir esas capacidades. Se conecta con el profesor del curso, Federico Brown, que está en San Pablo, que trabaja en la temática. Comenzaron a establecer la red, y pocos meses después de esa primera edición, ella pudo abrir un laboratorio con esos modelos de experimentación animal enfocados en detectar el impacto, por ejemplo, de la minería, que en Bolivia es muy fuerte, en la salud humana. Así que, de nuevo, encontró o pudo a partir de este tipo de actividades también generarse un lugar nuevo. Digamos, es interesante y nos parece importante compartir ese tipo de actividades. Es redescubrir. Cuando vamos ahí pudimos hacer visitas, tenemos algo programado gracias a Mauricio, que está programando algo similar para el domingo, una actividad, pero este tipo de escuelas nos permite conocer, visitar otros laboratorios e identificar, redescubrir estos colegas con enormes capacidades, por ejemplo, en seguridad alimentaria, trabajando en química de alimentos, en tecnología de alimentos, y son los socios naturales para la edición que sigue, que les voy a contar. A través de las autoridades, este tipo de eventos internacionales, como otros, no es el único, pero digo, este tipo de eventos también nos permitió conectarnos con nuestros representantes globales. Los instructores son, en ese caso, eran instructores de Brasil, Bolivia, Ecuador. Desde la universidad también se hicieron las gestiones para establecer el contacto con los embajadores, nuestros representantes en ese lugar, en Bolivia, quienes inmediatamente tomaron nota de la actividad, obviamente, y se sumaron a formar parte en la organización y en el sostenimiento de las ediciones posteriores. Entonces, vendrá una tercera escuela que va a estar exclusivamente con todo este aprendizaje, este recorrido que tenemos, conociendo las enormes capacidades que tienen en tecnología de los alimentos, en producción de alimentos, en las distintas etapas. La tercera escuela, que va a ocurrir el año que viene, en octubre, estará enfocada. La tercera edición en Bolivia, la cuarta escuela, muy bien, está bien, la cuarta escuela que va a ser en Bolivia va a estar enfocada en seguridad alimentaria, tecnología de alimentos. Es el aprendizaje después de 3 o 4, de 2 versiones previas, digamos, qué es lo que ocurrió y dónde es el fuerte. Ahora, en esta nueva edición, no es que desde el principio se pensaron en los alumnos, pero digo, ahora pensando en traer alumnos de toda la región. Lamentablemente, por los recursos limitados, en las 2 primeras ediciones, el 90% de los alumnos con los que contamos fueron alumnos que estaban radicados en La Paz. Bueno, la próxima edición, por todos estos apoyos que vamos a recibir de la universidad y de las embajadas también, la idea es poder solventar algo que nos pasó acá, que no pudimos, que lo va a comentar también Andrea, poder ofrecer ayudas para que vengan estudiantes por fuera de la localidad donde se organiza, que eso también nos parece clave, conectarlos, darle oportunidades para que lleguen al lugar. Estas escuelas también nos permiten conectarnos a otro nivel. Hablamos de formatos de educación. Muchos de los alumnos formaron parte también como entrenamiento, como evaluación final en la redacción de trabajos para journals en educación de las ciencias, básicamente, y en colaboración con la Academia Nacional la Academia Nacional de Ciencias de China, perdón. Vamos a lanzar este año en marzo, y esto también es un mensaje a los instructores de esta escuela. En marzo tenemos el deadline donde vamos a lanzar un número especial donde vamos a recopilar las actividades de laboratorio que se fueron desarrollando en cada uno de los lugares. Lo que hicimos en Bolivia ya está en marcha y con buen progreso y avance. Invitamos a los instructores de esta edición también a sumarse. Son textos relativamente cortos, pero creemos que el número especial va a sentar un precedente interesante para que se puedan replicar en otros contextos actividades similares. Luego de todo este tipo de este aprendizaje, este conocimiento, una cosita que no mencioné, es decir, a partir de la segunda escuela empezamos a pensar en, bueno, ¿cómo sería el progreso, el avance? Entonces dijimos, una futura edición en Bolivia definitivamente tenía que ser o tiene que ser orientada en la temática donde encontramos que hay un gran potencial y una fuerza intrínseca que serían estas escuelas en seguridad alimentaria. La segunda cuestión que nos planteamos inmediatamente es decir, bueno, a ver, ¿dónde más podemos empezar a replicar este tipo de actividades de nuevo? Porque cada lugar tiene su idiosincrasia, tiene su realidad, y entonces necesitamos seguir aprendiendo si queremos extender este tipo de actividades a todos los países del sur global. Y ahí es que surgió esta posibilidad en Chile, y ahora los dejo con Andrea, que nos va a contar en qué consiste la escuela que estamos inaugurando hoy. Muchas gracias.
Muchas gracias, Franco. Entonces, rápidamente voy a contar cómo va a ser el programa de esta escuela y algunos detalles. Primero, tenemos que agradecer a nuestros los que nos patrocinaron, ¿cierto? Primero fue la Facultad de Odontología de la Universidad de Chile, Facultad de Medicina, Facultad de Ciencias Químicas y Farmacéuticas de la Universidad de Chile, tuvimos el apoyo también de la Universidad del Desarrollo, junto a Mauricio Calderón, de la Academia de Ciencias Chilena, de la TUAS, la CREP, que es el partner regional que tenemos, de la Academia Brasileña de Ciencias y del International Science Council. Como dijo Franco, nosotros tenemos cursos en paralelo, voy a detallar a continuación, pero quiero mostrarles eso primero. Tuvimos 143 preinscriptos de diversos orígenes, ustedes ven, Camerún, Bolivia, Venezuela, Argentina, Uganda, Tunisia, de República Dominicana, Panamá, Nigeria, etcétera, varios países que desafortunadamente nosotros no pudimos invitar a estos estudiantes porque no contamos con recursos para los estudiantes, solamente para los instructores. Y por lo tanto, de estos preinscritos también quiero decir que de categorías tenemos docentes, un 11%, estudiantes de pregrado, la mayoría, 46%, eso nos alegra mucho porque realmente ahí queremos impactar desde la juventud, ¿cierto? 12% de postdoctorandos, 52% de estudiantes de magíster. Magíster y pregrado son nuestra mayoría de estudiantes en todos los cursos, y otros también técnicos de laboratorio, otros profesionales interesados en los distintos cursos, y ustedes ven, de los preinscritos tuvimos una mayoría de hombres, pero hicimos un esfuerzo para tener una escuela equitativa en la selección de los participantes, entonces estamos muy satisfechos con esto. Les voy a comentar que tenemos las sesiones de la mañana, las conferencias Magna, ¿cierto? Las Keynote Lectures. Hoy día vamos a partir con el doctor Steven Smith de pinzas ópticas. Mañana tendremos Calcium Signal con la doctora Cecilia Hidalgo, que además es presidenta de la Academia Chilena de Ciencias. El profesor Henning Ulrich de la Universidad de São Paulo, que cuando tuvo conocimiento hizo toda la cuestión de venir a participar con nosotros. Doctor Hernán Greco de la Universidad de Buenos Aires, que va a hablar sobre Open Tools, ¿cierto?, para ciencias, y una charla final de la doctora Carolina Santa Cruz, que es la representante regional de la International Science Council, y nos va a hablar de diplomacia en ciencias. Estas dos últimas charlas son online exclusivamente, nosotros vamos a tenerla el sábado, esas dos serán totalmente, la participación del sábado es online, incluso las evaluaciones para los estudiantes que estén aquí presentes, las evaluaciones van a ser enviadas con un formulario, ustedes tendrán que responder, son evaluaciones más bien del curso y de los aprendizajes generales, no tienen que preocuparse particularmente con esto. Y los cursos particularmente que tenemos son el de bioespectroscopía con la doctora Iraima Cordero, muchas gracias por su presencia. Mineralogía óptica, doctor Mauricio Calderón, aquí presente también. Fotoquímica, que va a ser una pequeña parte en ambos cursos de bioespectroscopía y de imágenes de calcio. Integración del metabolismo energético, muchas gracias profesora Patricia Sancán, profesor Mauro Solapena, que vinieron del alma mater donde estudié la Universidad Federal de Río de Janeiro, y el curso de imágenes de calcio en células vivas, donde participo yo, la doctora Paola Llanos, el doctor Pedro Lobos, doctor Jorge Toledo y el doctor Henning Ulrich también. Y finalmente el curso de pinzas ópticas, que está dirigido por el doctor Christian Wilson y que cuenta con la participación de destacados investigadores internacionales. Thank you very much for your participation, Dr. Are Masvaten, Dr. Steven Smith, doctora Karina Liu, doctor Christian Wilson, muchas gracias por toda la participación en la organización, y doctora Camila Correa, muchas gracias también por la organización. Ustedes ven, el programa asusta un poco, ¿cierto? Pero básicamente lo que les quiero decir que las mañanas son las conferencias, 3 días de conferencias presenciales, un día sábado de conferencias online, coffee break, y ahí entramos a los cursos. Cada una de esas líneas es un programa distinto de los cursos y nos vamos a tener que dividir. Están las salas ahí, pero al terminar acá nos juntamos afuera y voy a hacer una pequeña organización de los participantes para que sepan dónde tienen que dirigirse cada uno de ustedes, ¿ya? Ahí ustedes ven, tenemos varias clases teóricas y actividades prácticas incluidas. Al final de las jornadas tenemos unas sesiones de presentaciones y ahí sí ustedes van a tener que presentar algo de lo que nosotros hicimos en el laboratorio, analizando datos y mostrar lo que aprendieron. Eso es el día viernes, ¿ya? Y finalmente agradecer mucho a la comisión organizadora. Yo soy la chair, pero participaron doctor Calderón, doctor Franco Cabrerizo, que invaluable su ayuda, participación, entusiasmo, etc. La doctora Paola Llanos también fue mi brazo derecho, doctor Christian Wilson, doctora Camila Correa y doctor Pedro Lobo fueron fundamentales, además del staff, particularmente que Camilo por toda su ayuda y participación. El comité científico está integrado por mí, doctor Franco Cabrerizo, doctora Paula Denofrio, doctora Patricia Zancán, doctor Maro Salapena, doctor Iraima Cordero, doctor Mauricio Calderón, doctor Jorge Toledo, doctor Pedro Lobos, doctora Paola Llanos, doctor Edmundo Polanco, doctora Estela Alcaman, doctora Karen Quintanilla, doctora Mariana Cerveto, doctor Andrés González, doctor Pablo Cruz, doctora Camila Correa, doctor Christian Wilson, doctor Steven Smith, doctor Aaron Majavaten, doctor Henry Nulich y doctor Hernán Greco y doctora Carolina Santa Cruz. Entonces, no puedo dejar de agradecer también a los sponsors. Aquí estarán ahí afuera mostrando sus productos. Andes Import, Prion Lab, Tissue Diagnostics. También recibimos un apoyo de la Sociedad Chilena de Farmacología, representada también por la doctora Paola Llanos acá, pero preside la doctora Sonia Buvnik, y por Redeca, que nos ha entregado, ¿cierto?, todo su capacidad, microscopio, equipo, para que nosotros podamos hacer los cursos. Dicho eso, quiero invitar al doctor Smith a su presentación. El doctor Smith tiene un PhD en física aplicada de la Universidad de Twente y un grado en física de la Universidad de Washington. Él fue la primera persona que observó una molécula de DNA moviéndose por electroforesis y separó a través de electroforesis esta molécula, siendo un pionero en esta área de manipulación de moléculas únicas. Entonces, les dejo con el doctor Steven Smith con su charla Single Molecule Manipulation with Magnetic and Optical Tweezers. Thank you very much. Y mientras cambiamos la presentación, quiero decirles, por favor, aprovechando la convocatoria, que al final de esta jornada solicitamos que estemos todos ahí adelante para sacar una foto colectiva, ¿cierto?, para mostrar en las próximas versiones de la escuela y luego distribuirlos en los respectivos cursos. Muchas gracias a todos. Gracias, doctor.
Hola! I am Stephen Smith. It is a great honor that I was invited to speak to the young scientists of the future, and I want to thank the World Academy of Sciences and the University of Chile for inviting me here. I'm going to talk about the history of my career in single molecule manipulation. Let's see here. And I started out as a technician. In 1987, I was an electronic technician for a department at the University of Washington in Seattle. And I was studying at night for a degree in physics. And back then, gel electrophoresis of very large DNA, such as the chromosomes of yeast was important for my department, and also it was a good thesis project for my master's degree. Some slight difficulty reading my own slides here. Okay, I wonder if that could be shorter. Anyway, this is a picture of a fluorescence microscope looking at gel electrophoresis of DNA. And underneath the cover slip is agarose gel, and it contains lambda-phage DNA, which is about 48 kilobases long. That's 16 microns contour length. And it's hooked to a 9-volt transistor battery to make an electrophoresis field. These are immobilized molecules of stained DNA at different depths in the gel, and this is applying the electric field. As you see, they are moving toward the positive electrode in an interesting slipstick fashion. And what I wanted to know is, or what I was curious about, is this elastic behavior, the fact that they would stretch and then contract again. So I wanted to get my hands on these things or explore the physics, the forces that were involved. Now, DNA is, all its properties can be explained by its dimensions, its charge, and its flexibility. So it has basically three parts: the deoxyribose sugar, the bases, and the phosphates, and a space in between. And each phosphate has the negative charge. And it's quite flexible. That means that it only goes about 2 bases before it loses sense of direction. So its so-called persistence length is short, like 1 nanometer. The double-stranded DNA is 2 strands bonded together by hydrogen bonds, and it's got some holes in between the bases which want to repel water. That is, they're hydrophobic. And the phosphate linkages are stiff, have a constant length. So this problem with water could be solved, for instance, by simply stacking them at an angle. This would be flat DNA. That's not how it actually works with DNA. It fits better in a helix like this. It stacks better. And in this case, the persistence length of DNA is about 150 base pairs, which is quite a bit longer, or it's relatively stiff. However, stiffness is a relative description. For lambda-phage DNA, which is 16 microns long, that's 320 persistence lengths. It certainly makes a very random walk if you let it collapse. And the random size of that walk would be about 1 micrometer. And the mean end-to-end distance would be 0, because it could be walking to the right, or it could be walking to the left. Now, the operant theory of entropic elasticity at that time was the so-called freely jointed chain model, in which the force was the only thing that aligned. For instance, this over here is a model of the collapsed random coil. This is the chain extended out by some force F, and the alignment in a specific direction would give a delta X, which is in the direction of the force. And that, as it represents a certain energy, which we'll call the Hamiltonian, and this we'll call the partition function. And together, if I want to know what is the average cosine theta, I just integrate over the surface of a sphere with this Boltzmann factor, the energy divided by kT, the temperature. And that gives you a thing called the Langevin function, which is hyperbolic cotangent of force times the length of those little steps, which are called Kuhn segments, divided by kT. I was at a conference and I met Carlos Bustamante, who are familiar probably to some of you here. And then he was working at the University of New Mexico, and then he went on to the University of California, Berkeley. And he invited me to join his lab because we were both working on looking at single DNA molecules of DNA, single molecules in fluorescence. The first thing we made to explore that was called a magnetic tweezers. And that is a ferrite-containing polystyrene bead, which is attracted to a magnet, connected by biotin streptavidin connectors to a piece of double-stranded DNA, and then the bottom is connected to a cover glass with an antibody, and this is digoxygenin, an anti-digoxygenin antibody. So with this, we're able to pull on the DNA and extend it with some known force, which we could calibrate by using Stokes' law on the bead. So what we saw indeed was this is a schematic of the actual experiment. Under the slide is all liquid. There's no gel here. We can attract the magnetic bead to the right or the left, and there's also a flow running up and down the lengthwise through these tubes. And this bead can produce a very small force, less than 1 piconewton. And a piconewton is the force that it would take to lift one red blood cell off the table. It's the weight on the surface of the earth of just something as small as a red blood cell. This is a picture of the fluorescence picture of the bead in being influenced by the flow. The flow is vertical, and the magnet is pulling the bead to the right or to the left. With that, we could calibrate the force and compare it with the freely jointed chain model, which it did not fit. So our first discovery was that the model was not working for our polymer because these lines here are the various versions of the freely jointed chain, and the little dots are the data of force versus extension from the magnetic bead. So we were saved by the theorists who read our paper. The paper was in 1992 about the fact that it didn't fit, and in 1994, John Marco and Eric Sigia from different university figured it out that the freely jointed chain was not a good model for this semi-solid rod, which is DNA. In fact, the best model is called the worm-like chain. The worm-like chain is considering a flexible rod which has smooth bends in it, which are induced by the thermal forces. And at low forces, they have precisely the same functional form for extension, x, divided by the length, the contour length, L. So, you know, if it's a low extension, then it's 3 kT, kBt over the persistence length. But at the high extension, there is, the force goes up proportional to the inverse of the remaining slack, which is getting smaller and smaller. So x over L is approaching 1. This number is getting small. This force is getting big. And in the case of the worm-like chain, it goes as the square of that residual slack. A much better magnetic tweezers was designed and found by Benzimon and Croquet in France. They decided to not drag the molecule against the bottom surface, but rather pull it straight up towards some magnets. And they had a very ingenious way of calibrating the tension by looking at how much the thermal forces would deflect the position of the bead. So it has 1/2 kT average energy transverse, and from that we can deduce what is and how far it goes. We can deduce what is the width of the potential well and what is the tension in the chain. But another wonderful feature of this is that they can rotate these two magnets. They can spin them around, and the bead has a preferred magnetization direction, so it also twists. You can put twist in the DNA by rotating these magnets. And first thing they saw was that this is a graph of the fractional twist of the DNA, where 0 means it's no extra twist. The 0 is the native DNA in its native state, no extra twist added right or left. But when you start to twist it one way or the other, it forms plectinemes. That is, the twist is turned into writhe. This is something you can see with your garden hose as you're trying to wrap it up. It forms these knots. And this graph on the bottom is the how far up it goes, the height of the bead versus the twist. And when it forms the twist and it forms these knots, it pulls down low in either direction and in a symmetrical way. So it behaves like a solid rod, a flexible rod, a twistable rod, but still nothing unusual or terribly interesting. But if they raise the force, this bottom one is a low force, and that's why it doesn't go up very high. The next one is 1 picodalton is a higher force, and it turns out that in the negative direction, that is unwinding the DNA, it doesn't pull down on this side. In other words, it doesn't hold the torque, it doesn't form the plectinemes, it has a flat trace. And that is a discovery of DNA untwisting, melting, and failing to transmit torque. And then at the highest, when the magnet is low and the force is made high, such as 8 picodaltons, it doesn't form plectinemes in either direction. So not only do we have left-forming DNA, but we have some mysterious substance on the right, which is an abnormal form of DNA, which doesn't transmit torque above a certain amount. And they explored this by the magnets and by other means and determined that it was a case in which the bases had been excluded from the stack and they were now on the outside. And they named it pDNA for Pauling. Pauling had conjectured before Watson and Crick that DNA might look like this. Meanwhile, back at the Bustamante lab, we explored DNA by switching to optical tweezers. Optical tweezers work on the principle that light has momentum and it transfers force to matter. And this was discovered, well, actually, it was discovered rather long before Maxwell had his equations for electromagnetic radiation, but it was observed that the tail of a comet always points away from the sun, due to the pressure of light. But Maxwell put numbers to it, and here's an electric field with here's a light wave with an electric field vectors, magnetic field vectors, and this wave of light hits matter, and in the matter is this electron. I'm trying to explain how is it that a wave can push something? How can light transfer matter, transfer momentum to matter if light is a wave? It can, because the electron feels the electric field. It starts to move up and down. That's moving a charge through a magnetic field, and that produces a force which is perpendicular to both the velocity and the B field, called the Lorentz force, which in this case could be forward. So it is possible, if the charge interacts with the magnetic field and the electric field, to push it away. And in fact, the amount of pushing, the change in momentum is the amount of energy that's absorbed divided by c, or in photons, that's the momentum of a photon is Planck's constant times the wave number, or 1 over the wavelength. This theory was tested in 1901 by Nichols and Gordon Hall, and they confirmed by shining light on a torsion balance with little mirrors in the inside. And you can read more about that on Wikipedia. I don't think they published a paper that anybody can find, but at any rate, you can read about it there. In 1960, the laser was invented, and it was first a ruby rod, a pulse of light, and I was just getting out of high school then, and I took a tour of the Boeing company research labs, and they were actually hitting one of those torsion balances with pulses from a ruby laser to see if the radiometer would begin to oscillate. But more appropriate to the field of laser tweezers is the CW laser. CW stands for constant wave. The gas laser was invented by Javon Bennett and Harriet at Bell Telephone Laboratories in 1961. And also working at Bell Labs was Arthur Ashkin, who won the 2018 prize in physics for inventing the optical trap. And he worked there for 40 years, but he was using one of the lasers that they had invented there and looking for applications. His first paper was published in 1970. Is it possible to make some of these extra signs disappear so I can also read? Nope, that's not possible. Where am I? I pushed the wrong button. Sorry about that. Yeah.
Wearing another screen.
I'm on a different screen,
Yeah,
yes.
let me become.
Okay. My problem is, you see this? I would like to read behind it.
Yeah.
Perfect. Now I can read the sign at the top.
But now you have only. One second. Yeah.
Close enough.
Okay.
Can you still hear me? Good. Good. Sounds good. Okay. Arthur Ashkin builds the first optical trap, and I can read the caption. Yes. in 1970. And what he discovered was that if he had a solution with particles in it, such as glass spheres or polystyrene latex spheres, and shined a laser light on it, that they would become trapped in the laser beam and moved away from the source of the laser. And he also had a dual beam counterpropagating trap with two lasers shining from opposite directions that would trap a bead stationary in the middle there. Okay. Well, okay. The principle of this is that the light photons come in with some momentum, Pn, and they are refracted by this object in the water, this round bead, to some different angle through an angle theta, and they leave with a vector P out, and there's a difference between the direction of these two vectors. Here's the direction of the incoming, the outcoming. This is the difference in momentum. And as Newton said, for every action there exists an equal but opposite reaction. Here is a force or an impulse which represents this change in momentum in the opposite direction. So this bead is going to move upwards and forwards. This is a simulation of something that Ashkin did. This is a simulated beam of photons, and this is a simulated particle, refracting them. It works on, and these little white things are being scattered backwards, are reflections from the simulation. Okay, so it's a fairly now, what is peculiar about this? Okay, here is another thing which Ashkin discovered, which is that if you have a converging beam of light to a focus, that the bead will be trapped near the focus. However, if there was a yeah. Okay, I'm getting these buttons to work. Finally, there. Yes. This red arrow on the bottom represents a force which is applied to the bead, and it actually causes the bead to escape from this single beam optical trap. Here is a dual beam counterpropagating optical trap, which holds up a rather larger force. So a symmetrical trap is stronger, is my point. And this simulation also happens to show that the light photons are deflected. The green ones from the right are mostly, the green ones coming in high on the right are mostly deflected down on the left. Okay. Here is an actual movie of a polystyrene bead about 3 micrometers in diameter. It's being sucked and blown away from a glass pipette. So this glass pipette is blowing liquid out the end, sucking the bead toward it, and blowing it away. And you might have noticed that when the bead moves, the light also moves with it. Especially when the so you can see the light being deflected opposite to the way that the bead is moving. So the exit beam carries some information about the light force. If I could collect the light that came out of the back side of the bead here, and if I knew the angle of that light, and if I knew its strength in watts, W here represents the watts of light. C is the speed of light. N is the index of refraction of the water that surrounds it. And sine theta is this theta here. From knowing theta and the brightness of the light, I can know the force that's on the bead. So it's a good method of applying force and a good method of measuring it also. So here's an instrument that was made in Bustamati's lab. It's called the counter-propagating laser tweezers, and it works from two lasers that are shooting laser beams toward each other through some steering optics, including a polarizing beam splitter, a quarter wave plate, and a microscope objective lens, and it comes to a focus. This little thing here represents the glass pipette. On one end of the glass pipette is a polystyrene bead, and here is a piece of DNA that's connected to it. And in the trap is another polystyrene bead. So we can apply force to this molecule by pulling the pipette away from the trap. And the light that comes out from this laser is collected by that objective, goes through this beam steering optics, and ends up in this position detector. This laser does the same thing in the opposite direction. It's entirely symmetrical. So the deflection of the two laser beams can both be measured to infer the force. Doing this, we pulled on the DNA harder than we could have pulled on it with the magnetic bead. And we saw three interesting things. One is that this little curve right here on the red curve is the native length, that is native DNA being pulled up to 50 or 60 piconewtons in force and becoming about 8 micrometers in length. This is half of a lambda, so it's 8 microns long. And then notice this curve is the worm-like chain, and you can inspect it and determine that the persistence length is 50 nanometers, which is 150 base pairs. If you work on this molecule long enough, it becomes single-stranded. And that is this longer length curve in blue, which is longer because the strand is no longer twirling around the rod. It's now in a straight line. So it's also much more flexible. See how it has a more gentle curve that, whereas this is a sharp curve. This indicates that the persistence length is like 0.7 nanometers, which is just 1.5 basis. And then finally, this rather striking and unexpected lengthening of the DNA, it goes to some different form, which very well might be represented by that flat DNA that I was describing before. It's longer, not as long as a single-stranded, but it has a flat plateau, which usually means a phase transition from one form, a structural form, into another. And then it comes to the end of the transition, and the force goes quite high. When it comes back, these curves are mostly reversible, but there is this hysteresis right here, which indicates that part of the strands were melted or peeled back. But still, most of this is an alternate form of DNA, which was named sDNA, not by us, but by Cluzel et al. In France, who had a companion paper to this in Science. And here is my model for what the DNA was probably doing. That is, it starts out as B form. It goes into some stretched ladder form. they could be slanted. I had no idea what it was, except that these linkers on the edges had to be more or less not going into spiral anymore. And then from some nick or other, it would melt back. And then when you relaxed it, it would B-form DNA again, but there would be a delay of these strands in reannealing. So that would explain the hysteresis. There were computer simulations made about what it might look like. There's 3 groups that came out with rather similar results called a stretched S-form ladder. But there was some controversy about whether or not sDNA is a separate form of DNA. So, among other things, we would like to test how much twist remains in the sDNA. Is it perfectly straight, like 2 separate single strands, or is it somewhat twisted, like this S-form ladder suggests? So how can we test for the twist in sDNA? One of our graduate students was quite brilliant about this and is now a professor in Stanford in bioengineering. That's Zeb Bryant. He designed an experiment and made a molecule along with Michael Stone for a molecule that could be assembled to actually explore the twist. That is, this is a bead in an optical trap. This is a bead on the pipette. This is a piece of double-stranded DNA. This is another smaller bead, which is attached to a 3rd position. And there is a nick below this bead. So what this means is that this piece on the bottom can swivel freely. It can transmit no torque. This is like free swivel. This part here can build up torque. This part here can be overstretched as into sDNA. And when we do that, we can watch this bead spin. So it's quite an engineering feat to make the various, this has a fluorescein antibody tag, and this has a digoxygen tag, and this has an engineered nick, and there's a biotin here. So it was a big machine that Zeb Bryant made. And what you could also do with this is to test different amounts of twist by rotating the pipette. If you run a flow past this bead, it will not turn. It flies out like the rudder of an airplane or a flag. It flies at a certain angle and will not rotate. And then if you twist the pipette, you can wind up torque in this section. This is assembling the 3 pieces of this miracle molecule, in which this piece is the bottom big bead on the bottom is in the trap, the bead on the pipette's at the top, and the little bead in the middle is quite small because we want to see it turn rather fast. And then you twist this pipette with an electric motor, actually, very small electric motor, and watch it spin. So you can wind it up and turn off the flow and watch it go around. And if we want to test the overstretched transition, we basically pull on this on the extendable link until it starts to stretch, and then this bead begins to go around. But this is actually going up. Here's 16 times the speed. This is a time lapse of the bead moving, and you can see this bead extending. This bead at the bottom is under constant force feedback in the optical trap. That is, if the force starts to fall too low, the force detector knows it and it moves the pipette up higher. So a constant force is maintained in there, and that force was a little bit higher than the overstretching force of DNA. The overstretching force of DNA is about 65 piconewtons. And here is a graph of time is on the bottom. The black line is the force that was applied to this molecule versus time. Suddenly it jumps to 80 piconewtons, which is higher than 65. And this right here in the red line is the twist in the molecule is going down. It's unwinding. And at this time, the force was lowered to lower than 65 piconewtons, and the molecule starts to wind up again. Okay. And the molecule was getting longer, and suddenly it started to get shorter. So using this machine, you can make some measurements and determine that there is a difference in phase, that you could make a sort of a phase diagram between the S form and the B form, where if you pull harder, there's a slope to this. If you pull harder, it spins faster. So the coexistence of those two phases increases its torque when the tension in the molecule is higher. So it's kind of like one of those toys, which is called a run-run, which is a twirling object which you can wind up with string and pull back and forth, and it spins first one direction and then the other. But at any rate, it's a very efficient screw mechanism for converting linear force into torque. And in fact, many phases have been put to such a phase diagram. This is the P for Pauling phase. This is the Pauling phase of DNA under less force, so it supercoils. This is the B form of DNA. This axis is the torque in piconewton nanometers. This is the force that you're stretching it with. And here's all of the L form DNA. So if you pre-twist the DNA before you stretch it, but you hold the twist number constant, you get these curves which represent phase transition. As I say, every time you see a horizontal slope in the force versus extension curve, it represents some transition between phases of the DNA, between supercoiled P and P form, or between B form to the S form, or like that. Okay. So these not only have special names like B form or S form, P and L, they have a unique length normalized to B form. S form is 1.7 times longer. It has 33% of the twist of B form, so it has less twist. P form has a lot of twist in the same direction, and that's what turns it inside out, and it is 1.56 longer. And L form has a negative twist, and it's longer than B form. So it takes some of the helicity out. Okay, if we were to, you might wonder, is any of this of any importance in biology? And for the most part, no. These forces and torques are much outside the range of molecular motors, for instance, except, well, show you an example of phage packaging, which can pull with 50 piconewtons, which is sort of up there. But all of biology is pretty much in this negative supercoiled region right down here in the corner, which is supercoiled B minus, or straight B. This line represents zero torque here in the middle. And it intersects the S to B transition at 65 piconewtons, which is where DNA overstretches. Okay, so other mechanical things that have been done with DNA is to unzip it by various groups, just by pulling Watson and Crick strands apart and letting this spin. And what you find is that it unzips around between 15 and 17 piconewtons in physiological buffer at room temperature. And you get this pattern, which represents clumps of AT-rich region or CG-rich region in the sequence. And you cannot sequence DNA on a base pair scale. Some of these features are, for instance, 60 nanometers long, which is going to represent about 40 base pairs. So this is a very coarse picture of DNA, but on the other hand, it is a unique one. This has been unzipped and rezipped about 4 times, back and forth. It's repeatable. Another thing is about a reversible reaction like this, the force times the distance equals the change in free energy. So we can know what is the melting energy or the unzipping energy of DNA by doing this reversible reaction. Another thing that has been done is to package DNA in bacteriophage. This is a Phe29 bacteriophage, in which this bead at the top is in the optical trap. The bead at the bottom has got some ATP. It has a rotary motor at the inlet of this capsid head, and it pulls the DNA into it. If you have the constant force feedback that I mentioned, you would raise the pipette slowly, keeping the force constant. And in that case, by seeing how fast the pipette moves, you can know the speed at which it packages that DNA and whether or not it pauses, and what is the effect of more ATP or less ATP, things like that. Another experiment is do not let the pipette move, but just let the tension increase and see what the maximum force is. And this molecular motor in Phe29 can pull up to 50 piconewtons, which is almost enough to overstretch DNA. Here's another example of biology in which we have an RNA hairpin that's held by a couple of actually RNA DNA hybrid handles to a bead that's in a trap and a bead that's on a pipette. And we load onto the hairpin the NS3 helicase from hepatitis C virus. And this helicase with ATP will invade the hairpin and open it up. And you can see what the step size was, and typically it tends to, this is 60 base pairs, tended to do this in 10 base pair jumps, but the resolution was 2 nanometers, which was 2 base pairs, but generally you can see a larger jump. It can resolve a force of 1/10 of a piconewton. This opens up at about 24 piconewtons, but it would be held under a constant force feedback of 17 piconewtons. And you can, we say that the resolution in time was 20 milliseconds. And that's not because it takes us 50 hertz to collect the data, but because of thermal motion means we have to average the motion down to that level. We have to average all these motions together to obscure the thermal noise. We have to get down to 50 hertz bandwidth before we can actually see the steps. And here I give the example of a ribosome held in this is Christian Kaiser, who made this et al., who made this experiment of holding a bead on a pipette with a ribosome, a nascent protein, which is T4 lysozyme, 164 amino acids, which itself is being pulled by a DNA handle. And he determined that this protein had quite a different melting point or denaturing force when it was close to the ribosome. The reason I showed this example is that this is an extremely complex series of parts. You have to have the tRNA, you have to have the ribosome and all its cofactors, and it all has to work next to this extremely bright laser light. So it's important that that you have a handle that has a little bit of length. It's also important that this light be of a low intensity, and all the oxygen is removed from this experiment so that it can't form radicals that hurt the molecules. It is amazing to me that he could get it to work. But the point is that you can get real biology to work next to an optical trap. Okay, thank you for your attention to my talk. And this is all about old experiments. If you want to review some modern methods for optical traps, see this article in Nature Reviews Methods Primer, Optical Tweezers in Single Molecule Biophysics. This is only a couple years old, and it's great modern stuff. Okay, thank you.
Easy. Thank you for your presentation. I have a question because I'm thinking about the interaction strength between the molecules that you use for attaching molecules. I'm assuming that the force that you can use in your experiments are limited by the interactions, for example, for streptavidin binding interactions or the different interaction molecules that you use. So what about the limiting force that you can use for your experiments? The second question is how you can scale the behavior of DNA in terms of the properties of the polypeptide properties, in terms of the random walk behavior or the FJC model. So how different is the behavior of the DNA compared with a protein? Thank you.
For the first part of the question, we can usually apply up to 65 piconewtons through DNA tether, as it's called. And it's good to keep that tether. We seldom apply that much. You could apply more if you actually cross-link the two strands together. But usually our experiments are conducted at considerably less than 65 piconewtons. It is a useful transition in the optical tweezers because you can't see anything. There's nothing fluorescent in the tweezers that I'm using. I know I showed you some fluorescent DNA, but that's not typically how we do our experiments. It's usually invisible. And if you wanted to know that you have only one tether, you would pull it to 65, observe the overstretched transition, and then you know that you had one and one only. For the case of the polypeptide, people have traditionally used the worm-like chain model for the entropic elasticity of a polypeptide chain. That is, after the native protein has broken apart due to some pulling force, then at least the high force portion of it can be well fit by the worm-like chain. However, it has a sort of a condensation plateau, which could be formation of a molten globule at the low force, and that is not anticipated by the worm-like chain at all. And there is no theory or a model that fits that very well that I'm aware of. It's very complex. It would depend upon not only the sequence of the amino acids, but also the buffer. You know, if the buffer favors hydrophobic collapse, then this would be a rather high force plateau. At 1 or 2 piconewtons, it could, instead of going sloping gradually to 0, it comes in high and finally falls off at the end. So, and it could depend on not just the molecule, but the buffer also.
Hi, thank you for sharing your beautiful story with us. And I have a question regarding I work with biomolecular condensates, liquid-liquid phase separation of proteins and RNAs together. And I was wondering whether we can apply the optical tweezers to understand some of the viscoelastic properties of these liquid droplets. I don't know what, I'm not aware of whether it's feasible.
Yes. Well, there are viscoelastic properties almost to single molecules. They behave in a similar manner to fluids under some circumstances. More interesting, perhaps, with the optical tweezers is pulling tubes out of membrane walls. If you had a cell wall and you would approach it with one of these beads and touch the lipid bilayer and then pull it back, sometimes it pulls it into a long, thin tube, which itself is so thin that it's invisible. But it is a curious thing, and people do research on that. If you want to consider separating the fluids in that sense, you might find the gap between the two fluids, push the bead into it, and pull it back again, and see if you can pull some of it out.
Another question? We still have time for 1 or 2 more questions. Still, I have a technical question in the experiment of set volume. You say you twist the pipette, but also the bead that is holding the laser also will twist, or no? Because it's spherical. Then if you twist the pipette,
Yes.
the other bead will twist. How do you create tension on that?
Yeah. Well, remember that the swivel or the nick is next to the bottom bead. So the bottom, I don't care if the bottom bead spins. It doesn't matter. It's part of the swivel mechanism. But what does matter is that the little reporter bead, the tiny bead, must not spin when the top pipette is turning. That's the part. The top part is what we put the extra turns in. And we keep that little bead stationary, we prevent it from turning by running flow past it.
Okay.
Yeah.
Okay. Thank you. Last question. Okay, if no more question, thanks again, Steve. Thank you very much.
Thank you very much, Dr. Steven, and thank you for your attention. I would like to have you all here in front of the stage to the picture. After we have a coffee, and then we will divide the participants by course, okay? Vamos a tener una foto ahora aquí adelante, después vamos afuera a hacer un coffee break y vamos a hacer la distribución de los participantes por curso, ¿ya? La otra cosa que me faltó avisar es sobre pueden venir por mientras, sobre el paseo del domingo. Nosotros vamos a tener un paseo al Cerro de San Cristóbal, enseñamientos mineralogía óptica, y nos tenemos que reunir ahí en el Cerro de San Cristóbal. Van a llegar las informaciones por email, ¿ok? Vengan.
Además, también los dejamos cordialmente invitados para que puedan recorrer los dos sponsors, que está Andes Import y además está Pure Lab, para que ustedes puedan conocer sus productos y algunos regalos que les tienen.
Vengan, vengan.